actions are deterministic in the belief space, even though they are non-deterministic in the state space. So you get even more than that. Okay. So that's for just actions over belief states, causative actions over belief states, and this is your observation model I was mentioning. The possible percepts will be basically given a state S, there is a set of percepts it will give out. So for those, the probability that it will give those percepts out is 1, and for everything else, the probability that it will give that percept out is 0. And when you are in a belief state, you get a certain set of percepts, and then if a particular state, if there is a particular percept that's not present, and if you happen to know that when S is present, O will be present, okay, basically the model is this. S implies O, which means not O will let you say not S. That's just logic. I'm not doing abductive inference, I'm just doing logical inference. It's modest tolerance, right? So S implies O, not O means not S. So that's what I'm using to compute the result. So first I actually do the action, and then on the belief state to get the new belief state, and then filter out all the states that are not consistent with the observations I got. And whatever is left is the true belief state I'm currently in. And if I'm lucky, that belief state would be cardinality 1, which means I know exactly where I am. If I'm unlucky, then it's still non-singleton, which means I have more work to do. Okay, so that's that model. And then when you are doing sensing during search, then in essence, all you know is you no longer do A star search, you do a O star search. You have to do AND/OR graph. Because when you introduce a sensing action, for example, check whether the room is clean, then when you actually do it, it might be clean or it might be dirty. So all you know is after you do this sensing action, your belief state would get split into 2 possible belief states. It will get partitioned into 2 belief states, and you will know which one you are in at the time of execution. But right now I still don't know, because I'm thinking planning right now. You see what I'm saying? So now I have to go take this to goal state and take this also to goal state. So in general, my plan now no longer is going to be a line plan, but it will be a tree plan. Every time there is a sensing action, I'll introduce branch into my plan itself. Okay? So that's the interesting thing that happens because of conditional conditions. Okay? And one other thing, and then the state estimation, basically this one actually is really for this. And all they're doing is you start something and then you do some action and then you get some percept, and based on that you essentially filter out the state that are not consistent with those percepts. Okay? And in the case of non-deterministic uncertainty, state estimation is not too impressive, because you mostly do a bit of modest tolerance and remove some states, that's all. Okay? Whereas in the case of stochastic uncertainty, you change the probability of where you think you are. In that picture that I showed you, those were all essentially the distribution of robot's location over the 2-dimensional space is essentially represented by a bunch of samples. The distribution itself is represented in terms of samples, and it was doing particle filtering. Many of you may have heard of the word particle filtering. And what is particle filtering? It is essentially doing actions and recomputing its state efficiently. Okay, when we get to the stochastic part, we will actually talk a little bit about state estimation before doing palm defeats probably. And it turns out that the easy case is Kalman filtering, and the harder case is particle, when it's the nonlinear dynamics, you will have to consider particle filtering. That's what it was doing. Okay? And then let me just mention this also, which is repeated from past, which is that the issue of whether you have actions which are deterministic or non-deterministic is orthogonal to whether you have partial observability. In fact, you can, for example, do conformant planning of this kind, either when you start with state uncertainty and have deterministic actions after that. In the bomb in the toilet problem, the actions are deterministic. Let's assume that my hands are not shaking when I'm trying to flush the toilet. So the actions are completely deterministic. The uncertainty is because of the state. And it will only go crazier if my hands also shake. I'm trying to pick up this thing because I'm under major stress, and then when I'm trying to put it into the toilet, it will fall out and then go off. Right? So that's possible. Real life is hard. Okay? And so, today make sure that you're careful when you go into the toilet. But the important thing is that you can do conformant planning whether you have, non-deterministic actions or deterministic actions. It's just that the belief spaces, belief states can only reduce in size, never increase if your actions are deterministic. Get this into your head. If you don't know which states you are in, let's say you are in S1 to S10 and you do a deterministic action, you can only be in S1 to S10 or smaller subset, not larger. Actions themselves don't cause any uncertainty. Whereas when you do non-deterministic actions, they can both increase and reduce. Okay? And to the extent you want to make progress by reducing the uncertainty in the state, you should keep that in mind, that when you want to use a causative action to reduce the uncertainty, better use a deterministic causative action, not a non-deterministic. Okay, that's pretty much what is being said here and is also being said here. I'll stop here. Next class when we come, we'll look at the factored representations and how to basically do progression, regression planning in factored representations with both conformant case and conditional case, and then talk about heuristics. Okay.